All right, just in case you're somebody who is trying to explain this questions, we have a high jumper. And this might be something you see at like a carnival or something like that. This high jumper is jumping from the high height all the way up here with a gravitational potential energy of 10,000. And you know, the cartoonist that did this one didn't give us units. So let's give these guys joules of energy. And they start off with 10,000 joules of energy all the way up at the top. And they go down, 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 perfect form, and they land right in this bucket. And don't ask me what happens next. But the question is, could you figure out what all the missing kinetic energies are? And well, the question sort of seems simple. Let's just make sure that we've got this idea. In the bank, we have a total mechanical energy of gravitational potential energy plus kinetic energy right up there at the top. And it looks like the gravitational potential energy is 10,000 joules. And the kinetic energy is just 0. So the total mechanical energy seems to be 10,000. That's how much energy we've got in the bank. Now, by the time we get down to this height, only 7,500 joules are gravitational potential energy, which means that for a total of 10,000, how many are kinetic energy? If you did the process and you thought it through, 2,500 joules added to 7,500 joules is the 10,000. By the time you're halfway down, half of the energy has gone into kinetic energy, and you only have gravitational potential energy of 5,000 joules remaining. That means that half of the original 10,000 is now kinetic energy. And by the time we get down 3/4 of the way down, or 1/4 of the height of the original jump height, we're down to 2,500 joules of gravitational potential energy, or 7,500 joules of kinetic energy. And by the time you hit that bucket and you dive right in there with perfect form, and let's just put like some nice splash lines, now we've got 10,000 joules of kinetic energy. Now, we don't know how fast this person's going because we need to know more information. You can ask yourself, what's the piece of information we're missing? In this case, the piece of information we would need is the mass. And so if we were trying to figure this out, we could figure out how fast this person was going if we knew their mass. And people could say, well, we might know how much gravitational potential energy we had at the top. That's fine. But we don't know how high up this person is. And what we could say is that at the top, if we knew that mass that would allow us to calculate the kinetic energy, then we could figure out how high up this person is if we just knew their mass. Because we know the gravitational potential energy, 10,000. We know acceleration due to gravity near the surface of the Earth, around 9.81. And we could calculate the height as the only unknown there. Okay, so there's one nice challenge question. And then the other challenge question, a little bit of a problem solver, is, I'll zoom right in for this one, refocus. We've got this idea of a roller coaster. And we're leaning on a children's cartoon show here. This character, Ferb, has built a roller coaster that starts from 85 meters above the ground and has a height of 0 when it's up at the top. So if we made the most basic design of roller coaster, we're saying that the V, not a height of 0, a speed of 0 at the top, and a height, let's call this speed at position 1, and height at position 1, according to the givens there, is 85 meters above the ground. And by the time they get down to the bottom, the height would be 0, and the V2 would be I don't know what. And so that's the question that we're asking is, how fast is this roller coaster going? You notice that the roller coaster doesn't tell us the mass, or the problem doesn't tell us the mass of the roller coaster. And so we could start out by talking about this problem as a conservation of energy problem. We could say E total at the beginning, E total 1 equals EG1. Expanding it out, it's not E total 1 equals EG1. I don't have anybody helping me today. E total 1 equals E total 2, which means EG1 plus EK1 is equal to EG2 plus EK2. And based on the givens we have, we can say that, oh, it starts from rest, so the kinetic energy at the beginning is 0. It gets down to a height of 0, so the gravitational potential energy at the end is 0. And so we could expand this out. Mass times acceleration due to gravity times height 1 equals 1/2 mass times velocity at position 2, or speed at position 2, I should say, squared. And like I was saying, this cartoon doesn't tell us the mass of the roller coaster, but conveniently, there's a mass on both sides of this equation. So I could divide both sides by m, and while without the m, I can't actually calculate how much energy is present, I can use the idea of conservation of energy, recognizing that for a one-body system like this, the m's can cancel out fairly easily a lot of the time, and I can get AgH1 equals 1/2 V2 squared. And then I'm just isolating for that V2. So 2AgH1 equals V2 squared. I'm square rooting both sides. And if I wanted to sub in my values, I'd say V2 is equal to 2 times 9.81 meters per second squared times height 1, 85 meters. That is a ridiculously high roller coaster. But if you've ever watched the cartoon that this character is from, you'll know that things are ridiculous on this show. And I can say 2 times 9.81 times 85 equals the power of 0.5, our square root, is equal to 40.837 meters per second. And it looks like we had 3 significant figures way back when at the beginning. So about 40.8 meters per second. So that's one of the ideas that's present here. If you also wanted to play with some of the other ideas, like explaining how apples fall from trees relates to these concepts of law of conservation of energy, maybe that relates directly to the carnival jumper. Or there's this situation here where I was thinking one day about what would happen with my daughter as I was pushing her on the swings, and how fast would she have to go in order to make it all the way around? Well, this is kind of a thing where I'd have to know some information about a swing. It reminds me a little bit of pendulum problems, but a pendulum that goes all the way around. I would have to know how fast would she need to be going here to make it all the way around to get over here. Well, I think the critical speed would have to be where she just barely makes it, where this is just 0 meters per second. And so how fast would she have to be going at the bottom if V2 was 0 meters per second? Well, if I'm thinking of this as a conservation of energy thing, I would need to know how long the support chain or support rope is for the swing. So let's just say that this was a 2.0 meter rope. At the bottom, she's 2.0 meters below the support bar, and at the top, she's 2.0 meters above the support bar as this thing goes all the way around a circle. So that means that the height difference is 4.0 meters. And again, this is just like a roller coaster problem, where I would say EG1 plus EK1 equals EG2 plus EK2. And for a 2 meter long rope swing, I could say, well, at the top, the kinetic energy would just be equal to 0. And at the bottom, if I call the bottom a height of 0, the EG would just be equal to 0. And that would mean, again, that this fits a very familiar pattern, that even though these situations, high jumpers, roller coasters, swings, all seem very different, in reality, there's a pattern that emerges. So I would say 1/2 mv1 squared equals mass times acceleration to gravity times height 2. And again, even if you don't know the mass of my daughter, or if we wanted to figure this out for any kid, regardless of whether it was my child or your child or a sibling or whatever, notice that there's a mass on both sides. So this becomes a mass-independent problem. It doesn't matter the mass of the kid. Really, the only thing that it depends on is acceleration due to gravity, and we'll assume that we're always going to be on swings on Earth, and really the length of the rope. And that's what's going to vary from one swing set to the next. So if I wanted to know how fast the kid has got to go at the bottom, it would be V1 equals, take the 2 from the 1/2 over 2 H2, square root both sides, and I could figure out how fast they would have to go, where this H2 value would actually be twice the length of the support rope for the swing. Anyway, this is just a few for fun problems, thinking things through, not exactly homework, but some brain scratchers, and I hope that helps.